it is time for our first speaker, Piotr Padlewski, to take the stage. He says he eats C++ for breakfast, and with contributions to Clang and whatnot, I am more than willing to believe that. Piotr Padlewski.
Right. Thank you very much. Yeah, so I come here to talk about story about autonomous drone racing. I changed slightly my interest since like last time I was here. I still eat C++ for the breakfast, but I moved into more of like machine learning. So right now I'm working at Google Brain. But here is a story about the project that I was working before joining Google. So probably when you think about drones, something like this comes to your mind, or maybe something like this. Today, what you're gonna see is I'm gonna talk about toys like that. So those look like much more beefy, and they are much faster. In the end, I will also talk about some even bigger drones. Okay, so what is drone racing? Drone racing is very new sport. It started around 2013, and basically people race with the drones. The drones transmit low latency feed from the camera. So the drones has a camera, they have a video transmitter. The quality of the feed is like very bad, but this is because it's analog. We want to have like as low latency as possible. And the pilots fly with goggles so that they can see what drones is. That's why it is called FPV, first person view. And the drones are pretty fast. They can go like up to 200 kilometers per hour. So yeah, they are pretty fast. And they are also quite cheap. Considering that the smallest DJI drone or like the smallest that you should buy is like $400, then this kind of range is not that big, but also you crush them a lot. So every time like someone asks me how it is to actually like pilot one of those, I say this is like piloting jet. So you're like in a cockpit and you fly very fast, very often low to the ground, and you make maneuvers on the track. So yeah, the drones are usually quadcopters, which have 4 propellers, and they're made of the frame is made of carbon fiber, so that they are very rigid and stiff. And maybe let me tell you about like how the drones actually work. So you probably all know that the propeller spin, the drone can fly, but did you know that the drone can actually like fly in every axis, which means that it can fly this way, and this way. So how to make drone fly this way? Well, it's quite simple. You just put more power on the back, and it starts flying like this. When you want to go like this, just put more on here. But if you want to do like this, then that's quite tricky, but you just put more on one of these, because the propellers are going other direction, because if they would be going like the same direction, the drone would start spinning. All right, so let me tell you a little bit how the racing actually works. So there are a couple of different like leagues or competitions. The biggest is MultiGP, and it pretty much has like you start with your own drone. It has no limits to the power whatsoever. But the thing is that it's pretty hard to watch it. Like, okay, can you put the audio maybe? You have audio?
Audio is on the separate jack 3.5, so we have to plug that in.
We have it. Okay, yeah, but as you can see, like it's a lot of things going on. The quality is not so great on the video feed. This is what the people on the Google see. So there is also another league called Tron Racing, and this is much more professional organization. It has a lot of funding, and they figured one simple trick how to make Tron Racing more appealing. You know, they just firstly they have all the people have the same drones. They are much heavier and also slower, so that people actually can follow what's going on. And the most importantly, they have a lot of LEDs. So this is how it looks like. I'm not sure why we don't have a sound. But, yeah, so as you can see, like there is much more happening, and it seemed much more appealing to watch. Okay, and this is how the drone looks like. As you can see, there is a lot of LEDs, but like pretty much all of the other components are the same. People also fly something called Freeside and long range, and this is less about racing. This is done on very similar quads like this. So usually what people race with is quads that have the propeller size of 5-inch, which is something like this. If someone wants to fly for a longer time, then they can go for like 6-inch or 7-inch, because then it's much better for the battery. And if you ask me like how it is to pilot drone freestyle, this is something like this, just like base jumping in the mountains. So people usually use those drones to do some cinematic action flying. There is much more going on like these days, like National Geographic and like Discovery Channel. They all make they all hire like professional drone pilots to fly in the jungle, like in the trees and so on, just to make very good footage. And I can show you like one of the cool footage that you wouldn't be able to make with like any helicopter or like any DJI drone whatsoever. Okay, so maybe let me show you a small demo, but I will need one volunteer. Is anyone volunteering? I will tell you in a minute. Someone? Okay, I have one in the back. Come on, please come. Okay, give her a round of applause, please. All right, so I'm not gonna fly in this thing because this is too dangerous. But I have something like this. This is much smaller drone. It's pretty safe, trust me. And the thing is that about regulation, like flying FPV, which is like with the goggles on, it's not like legal, I would say. The problem with regulation is that you need to have a line of sight. You need to see the drone to be able to fly it. So what usually we do is that we have a spotter who see the drone and can take control over the drone in a case of emergency. Are you able to do that?
I think so. Yeah.
Okay, yeah, very good. You see, he's a professional pilot.
Welcome to OpenTX.
Okay, so let me set up the drone. Okay. So, I lied to you a little bit. Like, this is actually legal to fly, because this is much lighter. It's like also kind of stupid about regulation. I could actually fly it on the airport, like in the airport. But yeah, the regulations about the drone regulations in general is doesn't make much sense in some of the things. Okay, so let me tell you then about the autonomous drones. So how it started? There was a competition that was announced with a very big prize pool, $2 million, and it was about making artificial intelligence that could fly the drone on a racetrack. What we have is that we won't gonna get the drone, we're only gonna get the simulator, and this is quite hard. Okay. So the problem with transferring from simulator to real is that firstly, like simulators are never perfect. And the other thing about AI is that AI loves to exploit all of those imperfections and bugs. I'm not sure if you heard, but there was this very famous research done by DeepMind where they trained agent to play some very old video games, and what they found out that in some games AI found to like some small bugs in the game, and just like started exploiting it, for example, to get like many lives or so on. And there are other things like hardware setup need to be the same as in the reality. So there is a lot of things that needs to get right. By the organizers, also by the people who write the AI. So how it started? So Carl, posted a post on Facebook saying that he's looking for teammates. This was somewhere around like 3 weeks before the deadline, which is like the competition was announced like, I don't know, 3 months ago, 3 months before that or something. But okay, like Carol actually managed to get 36 people. Now we have 5, all from University of Warsaw, which I was studying at the time. The name is Mimotars, which is because our faculty is MIM. And what it turned out is that it was really crucial to get people with very, wide range of skills. Like Carol knows how to program our weird autonomous planes and things like that. Or like Pavel is excellent at machine learning. I was good at C++, and we were writing C++, so why not? And Michał is like math genius. Jacek is very good at physics, and also robotics. So it seemed like a Uber team. So let's do this. And the first task for the deadline was, make a video about the team, also detect a gaze on the image, and also fly the drone through the track. So making a video is quite simple. What about gate detection? So what we got is we had like around 8,000 images of the gates. We had to detect flyable corners on a gate, return confidence, and also like make it as fast as possible. The best solution, what many teams figured out, is that we need to actually relabel all the data sets because it was like very bad. So we also like made some special tool to do that. And in the end, what we figured out is, okay, like we're just gonna use some machine learning neural network called ResNet, just to return 8 floats. And it worked quite well. How about flying the drone in simulator? That was the last task. That was the hardest task to qualify. What we got? We got usual readings from the sensors like gyroscope, accelerometer. We also had the distance from the ground because like the drone had some sort of rangefinder, and we also have a camera feed and also coordinates of each of visible gates on each frame, so that we wouldn't need to do any sort of gate detection in this task. Okay, so I have like a question to you, like how would you approach such a problem? Like, do you have any keywords that you think like would be useful in such a problem? Anyone? Okay, I see there's not many drone experts here. So let me show you, like, make a few steps back and show you that this kind of problem can be tackled like with very simple solution, like building on top of very simple thing. So imagine that you need to program cruise control, right? So like in Polish, it's called tempomat. So you could think about like, okay, what about like machine learning model? It's like, okay, we have a speed, we want to get some certain speed. Probably, very sophisticated machine learning model can figure this out. You could also like think about, calculating how much power do you need for each to accelerate to certain speed and so on. But all those things are pretty hard, because like either you need to have a lot of measurements to make it very precise, like weight of the car, or like if you are going downhill or something, because it's all gonna change, right? And the simplest solution that works the best for something like this is called PID control. Whoever heard of PID control? Okay. So this is a very simple mechanism which is like a control loop. It is trying to reach some certain value that we want. So it's at all the time it measures what's the error rate, what's the difference between this certain value that you want to achieve, and it tries to get there by changing some other value. And PID stands for like the proportional integral derivative, which is like those three components that decides how much we should, for example, accelerate in the case of the cruise control. Okay, so let me show you how you can actually fly the drone only with PIDs. So suppose that you want to fly on a certain height, right? What you can do, we have this rangefinder, right? And like in all of the tasks, what we had to do is we had to control the drone like we would be controlling with the sticks with the controller, right? So we didn't need to like put certain power on each motor, etc. So by just making more gas, like giving it more throttle, it should race, right? So we're gonna make a PID control for a throttle, right? Just like say, okay, we want to be at 2 meters, so it starts and just wraps up and stays at 2 meters. That's very simple. How about if we want to fly with certain pitch? Let's say that, okay, you want to fly with pitch of 30 degrees. Then, we just made a PID controlling pitch. So whenever the drone is like at 0 and needs to be at 30, then it will just output more power at the end, or just like move the stick on the controller, and it should start flying at a certain pitch. But won't the drone go down, right? Because like if we have it's a certain power of the motors, and then we start pitching, then it will go down, right? We need to have actually more power to actually fly at the same height if you want to have it with pitch, right? But actually not, because when the pitch pit will start to pitch the drone, and the drone will start going down, then the other pit will actually figure out that, okay, we need more power, right? So it will just go and it will stay at the certain height. Okay, what about flying at certain speed, right? So let's say that we have some sort of measurement that gives us what kind of speed are we flying with, And this is more tricky because we actually need a pit on top of another pit. So we're gonna have a pit controlling a set point of the pitch pit. So let's say that, you know, the drone is stationary. We say, okay, fly with, I don't know, 60 kilometers per hour. So it is 0, so we start pitching, and until it reaches 60, it is pitching more and more so that it finds the right spot, right? So it just controls, like, it tries to figure out how much pitch it should have in order to fly with certain speed. So this is, I think, like, genius simple solution that you can, you know, do very hard task like flying a drone. Okay, so we know how to fly a drone, you know, with certain speed and so on. We know how to control it. How are we gonna fly through the track? So, you know, it needs to be able to make some sort of turns, etc. And we figured that we're gonna do some simple strategy, like, so whenever we score one gate, we're gonna have the strategy that says how drone should behave on the next gate. So for example, if the next gate is on the left, we're gonna say, okay, like, pitch a little bit so that it's gonna start turning until, for example, it reaches, it sees the gate. Then patch it for like 0.2 seconds, and then maybe like slow down before the gate so that we'll be able to see it actually. Okay, how about flying through the gate? Because we also need to, you know, somehow control the drone to actually fly through the gate. And the other thing, the simplest thing is just, you know, fly the gate perpendicular to the gate, right? So we need to just position the drone perpendicular, and, you know, just fly through it. And how we could do it? We just, you know, just look at all of the corners. We just see the projection, right? So if we see that, you know, those two corners are bigger to each other than this, then it means that probably the gate is something like this, right? And the nice thing is that we only need 3 corners to do that. And most of the time, because we are flying very fast, we won't gonna even see 3, but we only need 2 to make ourselves perpendicular to the one edge. And the thing we know about the thing about this task was that we knew of the orientation of the gates, so we could cheat a little bit. All right, so let me show you how we did in this task. This is a flight from a simulator. So as you can see, like, we are not even seeing the gates. We're just like trying to, you know, fly it as fast as possible. And, you know, sometimes it gets into this kind of oscillation. This is mostly because we didn't tune the pits, or we didn't have much time actually to do that. Just like we started 2 weeks before deadline. And this is how we did the whole thing. Okay, and it turned out that it gave us 3rd place. Like in the whole competition, there was like 400 teams with over 2,000 people, and, you know, somehow, like, our team, who started like pretty late, managed to get this 3rd place. So, and only 9 teams from the whole world made it to the next stage. Okay, the next stage was getting some hardware, because we knew, like, in the task, in the first task we were just using the simulator, but in the actual finals we're gonna use the real drones, and in order to, you know, to tune our algorithm at least a little bit, we get some hardware. So we got the workstation with the simulator, and we also get this sort of part that had 4 cameras. Okay, and we also knew that on top of the drone we will have NVIDIA Xavier, which is this small computer that has a lot of power. It has a lot of like GPU power, and also like a little bit of CPU power, so that you can pretty much run your machine learning models on, and, you know, do some robotics. The next thing was, flying to 4 competitions in US with like 5 people in team is quite expensive, right? So we managed to get the sponsor, which was RTB House, and it was very crucial. Like we talked with many companies, and only RTB wanted to sponsor us, and they actually sponsor all of our trips. Okay, and we started preparing for the competition. We figured that the simple algorithm that I told you about, having different strategy for each gate, that was very simple. It worked, but for the actual drone, we want to have something more sophisticated. So we figured that we want to firstly find some sort of lines and curves, how we should fly on the track, and then try to follow it. How we gonna do it? Bit controllers, pretty much. So whenever like the drone was not flying on the path that we wanted to, we just had a PID that was controlling the drone so that it stays on the path. So it's like, it speeds all the way down. Okay, how we gonna figure out where are we? There is something called dead reckoning. This is a very clever technique, which is, imagine that you have closed eyes and you're on, some sort of platform, and someone moves you in one direction. You can feel that you're accelerating in one direction, then maybe like slowing down, right? So even without looking, you can figure out like how much did you travel, or like how faster did you accelerate. And we can actually do the same thing on a drone because it has a gyro, it has accelerometer. So we implement dead reckoning. But the problem with dead reckoning is that it gets way off like very quickly. This is mostly because we pretty much like integrate, the errors like accumulate like very fast. So we need also another technique. Like dead reckoning is awesome, but this is very good only in a like very short amount of time. In a short amount of time, it is very good. So we also enhance much more ML models to detect the gates, and then when we know where are the actual corners, we can actually compute where we are in the space, knowing where are the gates. So what we did is pretty much, okay, we are trying to figure out where are we with dead reckoning, but when we see the gate, then we are calculating, okay, you thought that you are there, but we are here, so just reset it here. Okay, then what we did is we flew to the summit, which was on 16th of July, and when we saw how big are the gates, it's like, okay, we didn't expect that. I mean, we knew how they're gonna be, how big they're gonna be, but seeing it live makes much more difference. And we thought, okay, like we can probably fly through this, like this should be big enough. But then we saw the drone. Okay, it turned out that the drone was also very big. Okay, so like this thing has like the propellers of 5 inches. I think something like this had like 7 inches. So this thing was pretty much the size of the inner cage inside. And the drone also is very heavy. It was, I think, around like 1.6 or 3 kilograms, but it also has a lot of power. This was a prototype back then. Right now it looks much better. And on the first and second day, it turned out that there was like a lot of technical difficulties that we thought of. Like it is really very hard to take something that flies in a simulator and make it fly in the real life, even with like very good simulator. So on the first day, like nothing really worked. Like we didn't even manage to to take off. Fortunately, we had a professional pilot that was flying the track, so we could gather some data. And then after making a lot of hotfixes, just like, in a simulator, the axes are like X, Y, Z or something. Why on the normal like regular drone they are upside down? Okay, so we need to like figure this out and like also like change the degrees from radians, and there's a lot of hot fixes. And what we did is we've actually managed to autonomously take off and land, which is we were pretty much the only team who did that on that summit. And then on the third day, we figured that okay, we're gonna do something. We're gonna score the gate. Why not? So let me show you a video how it looked like. Fortunately, there is no sound. Yeah, but here you can see like the drone actually flew the gate. Like this is the first time the organizers all like saw that okay this actually can fly. So okay. So then because there was like a lot of technical difficulties, the competitions actually were moved like 2 months. Like when I was sending this talk, I thought that this is gonna be all over, but it's not yet. So there was the first competition in October, and it was epic fail. Like let me show you like we didn't even took off, but the other drones were doing like some weird things. In our case, what we figured out is our drone thought that it's like 4 kilometers off from where it should be, because we had a bug, and also there was like some bug in the software. So yeah, there were a lot of crashes. One team managed to actually fly 2 gates. The track was very simple, like it was almost like a straight line. So yeah, one team like just like flew almost straight and managed to get 2 gates. One other team get 1 gate. Most of the teams ended up on 4th place, which is like the last place, like no gates at all. Of course, including us. So yeah, that was epic fail. In the second competition, which is in November, it was actually not so bad. So yeah, the track was also very similar. We are the pink one. So firstly there was a team from UZH, and yeah, didn't fly much. It's pretty sad we don't have a sound. Like they make this. They had this Terminator soundtrack in the background. So yeah, we managed to fly 1 gate. Second gate, and then we couldn't find the other gate, so but it turns out that it was good enough to get the 2nd place on this competition. So like when the organizers were like announcing this, they were thinking like, oh, like the first team who's gonna win like gonna get $1 million, but also if you're gonna be the human, you're gonna get like even more. It's like everyone's like, not gonna happen, not this year. And the last competition was very yeah, it was pretty much on November 15. We didn't also do like very bad either. We also like managed to get the second place. As you can see here, like one team actually managed to fly the whole gate, the full track, and it was very fast. Like they managed to get the whole track in the same time we did 2 gates. But as you can see for like other teams, it doesn't look as good. The finals are coming up on December 6th. We are working very hard. There is actually a lab somewhere in Lockheed where we can test actually the drones before flying, which is like this one thing like made a lot of difference. So until December 6th, we are trying to prepare for this. And yeah, you can follow our story on the Facebook also. And so this is all I have, unfortunately, for this. I thought I'm gonna come here and tell you how we won $1 million, but not yet. And with that, I'm happy to answer all of your questions. And also, if you have any tips for us, that would be great. So thank you. Right. Okay, there is a question there, near the camera.
Hey, I got a lot of questions, but let's start maybe with the simplest. How are you developing that? Because you don't have a drone, so I understand everything is like offline. I understand right now you can test it in Austin, like offline, not being there. Yeah.
Yeah. So what we got is we got the workstation with like this Xavier, so we can test our algorithm and like on the real hardware in the simulator. So at least we have the same kind of compute power, so we can test how fast are we going, how fast are our algorithms. But unfortunately, we don't have any kind of measurements of like real flight controller and motors and things like that. So yeah, we are pretty much testing in a simulator.
And at the beginning,
Uh,
the first stage.
on the first task,
Yeah. That was
the simulator was open source, like it is open source. So they just built a track in it, and yeah, we just created a very very simple autopilot. So yeah, it was all done in a simulator.
and then you went to United States, yes, and you didn't have any prepared software.
No, we had we already had the something that was flying in a simulator, but this was the first time when we actually saw the real drone, and there were a lot of problems with how the integration between the real drone and the simulator.
And the other teams are from United States or the whole world?
So I think there is like 2 teams from Asia. 1 or 2 teams or like 3 teams from Europe. There's like the one that is the fastest right now is Mavlab from Netherlands. Yeah, and there is 1 team that it's like a remote team. Like there's some people in Asia, in Sweden, and in the United States. So yeah.
Okay, congrats.
Thank you. There's 1 on the back.
I was wondering if you were programming on, let's say, bare metal on a flight controller or on top of some Betaflight or something like that.
So in this case, the drone already had like the normal drone stack, I would say. So it had a flight controller with, I think, Betaflight. So what we actually were doing is we are just giving these input sticks, like we were just controlling with this kind of thing. So yeah, there was a layer on top of that, and we were just sending the signals.
Okay, and the flying mode was like more like acro or self-leveling mode?
So this was acro. They at some point they were thinking of making it stable. Okay, so maybe let me tell others what's acro and what's stable mode. So when you fly drones like the consumer drones, they're in a stable mode, which means that when you don't do anything, they probably like stay in one place. When you just push it front, it's just gonna start flying front. But when you put back, it's just gonna start. It's just gonna level itself, right? In acro mode, this is a totally different story because when you give a stick, it starts rotating like this. Okay, so this is more like acrobatic. So you only like give a very short movements so that you can put your drone in a certain angle. Yeah. So in this case, we're flying with the acro.
Thanks.
Mhm. Right. There is one bug or not? I cannot see. Okay. Oh, okay. There is one here.
Please raise your hand again so I can find you.
Yeah, there is one on the front.
Hey, you said a lot of stuff about machine learning models,
Mm-hmm.
but as far as you showed, everything is done with PIDs. So what do they do?
Exactly. I mean, this is so. Firstly, when I was thinking about doing something like this, my first thought would be, oh, just make a cool reinforcement learning agent, and train it to fly on such a thing, and this might work, but some people tried it on the qualification, and they ended up with nothing. Like maybe if they would have more time, they would figure something out. But right now, like everyone flies pretty much with the PIDs because this is what like you have much more control over it. For the machine learning models, we had to have something that detects gates with very high precision and also like very fast. So we tried a lot of techniques. Of course, we tried not to use machine learning models if we could, because I mean they sometimes doesn't work, right? And you don't know what's going on. And the only thing you can do is like either change the model or throw more data at it. So in some cases it didn't work well. So we tried all the computer vision, other computer vision techniques, but in the end it turned out that using research from pose estimation is the best. The pose estimation is like you have you are making picture of the people and you try to figure out what's the pose of there. And it turns out that yeah, this works very good.
Okay, thanks.
Right. We have a couple more of minutes more, so if there's any more questions. Right, I don't think there are any more questions. So thank you very much.